All right, let's dive in. I want you to just think about your phone for a second. Every time you scroll or tap or send a message, it's all powered by code that's making billions of tiny little decisions. But how? How does a machine, something that's just circuits and wires, actually make a choice? We're going to break that down right now.
I mean, it seems crazy complex, right? When you're just scrolling through your feed or logging into an app, your phone is making millions of decisions every single second, faster than you can even blink. But here's the thing, it's not magic. Behind all that speed is a set of rules that are, well, surprisingly simple. And once you get them, you'll pretty much understand how all software thinks.
So, here's what we're going to cover. First, we'll look at the basic idea of how code makes choices at all. Then, we'll get into our first and most important tool, the simple if. After that, we'll figure out what happens when the answer is no using something called else. We'll even tackle how code makes decisions with text, not just numbers. And finally, we'll see how you can stack all these simple pieces together to build some really complex logic.
Okay, so let's start with the big idea. At its very heart, a program making a decision is really just like coming to a fork in the road. Instead of just blindly going straight, it can actually pause, look at the signs, and decide, should I go left or should I go right? In the world of programming, we call these critical decision points, these forks in the road, control structures.
And this idea, it's everything. A control structure is what turns a program from just a dumb to-do list, do this, then do this, then do that, into something that feels alive, something that can react and adapt. It's literally what gives software the appearance of being smart, and it's the foundation for, well, everything else we're going to talk about.
So, how do we actually build one of those forks in the road? Well, the most basic, most fundamental tool in the entire programming toolbox is something called an if statement. And yeah, it's pretty much as simple and as powerful as it sounds.
So here's what it looks like. It's actually beautiful in its simplicity. You just start with the word if, and then you give it a condition. Now, condition is just a fancy way of saying a yes or no question. That's it. If the answer to that question is yes, or true, as we say in programming, then the computer runs the indented code right underneath it. But if the answer is no, it just skips that whole block and keeps on going.
Okay, so how do we ask those yes or no questions in a way the computer actually understands? We use these things called relational operators. Think of them as the basic tools for comparing stuff. You can ask, is this number bigger than that one? Or is it smaller? And this is a big one. You can ask if two things are exactly equal. And see that double equal sign? That's super important. It's different from a single one. Or you can ask if they're not equal. This is the language of comparison for code. Let's make this real. Imagine a simple program that figures out a student's average test score. It asks just one question. If that average is 95 or higher, then it prints out congratulations, and that is a great average. Now, what if the average was, say, a 92? Well, that condition isn't true, so the program just skips right over those print statements. It does nothing and moves on. But that brings up a really important question, right? The simple if is great when the answer is yes, but what about when it's no? What if we want the program to do something specific when the condition isn't true? For that, we're going to need another tool.
And this is the perfect way to see the difference. An if, by itself, that's like a one-way street with an optional detour. But an if-else, that's a true fork in the road. The program has to choose a path. No matter what, one of those two blocks of code is going to run. It has to go left or it has to go right. There's no skipping the decision. And here's what that looks like in the code. We have our if with its condition, same as before, but right after it, we add the word else. You can think of the else block as the otherwise plan. If that first if condition turns out to be false, the program just automatically jumps down and runs the code inside the else block instead. Here's a perfect real-world example, calculating overtime pay. A payroll program has to ask a simple question. Did this person work more than 40 hours? If the answer is yes, it runs one piece of code to calculate their pay with overtime. Else, which covers everyone who worked 40 hours or less, it runs a different piece of code for their regular pay. See? Two different situations, two totally different paths.
Okay, so up until now, we've been talking all about numbers, right? Test scores, hours worked. But what about text? Can a computer actually make a decision based on a word or a password? Oh yeah, absolutely.
I mean, you do this every single day without even thinking about it. The logic behind a password check, it's just a simple if-else statement. The program asks you for the password. If what you typed is exactly equal to science, then boom, you're in.
else for literally anything else you could possibly type, you get the wrong password message. That's all it is.
Okay, but that brings up a really interesting question. How does a computer know that Sammy is different from Summer? I mean, we can just look at it and see the last letter is different, but a computer doesn't have eyes. It only gets numbers. So how does it compare words?
Well, the secret is this really clever system called ASCII. And here's the big takeaway. Computers don't actually store letters. They only store numbers. So ASCII is basically a universal decoder ring. It gives a unique number to every single character you can type on your keyboard. Uppercase A is 65. Lowercase a is 97. The digit 0 is 48. Everything has a number.
So when your computer sees the string ABC123, it doesn't see that at all. What it really sees in its memory is this list of numbers: 97, 98, 99, 49, 50, 51. And here's the key. Once everything is a number, the computer can compare them just as easily as it compares anything else. It basically turns a word problem into a math problem. That's the whole trick.
All right, so we've got our basic building blocks, right? The if and the if-else. They're like our fundamental Lego bricks. Now we get to the really cool part. We can start stacking those blocks on top of each other to build way more complex logic.
Think about a bank trying to decide if someone qualifies for a loan. It's not just one simple yes or no question. There are a bunch of rules. In this case, to qualify, a customer needs two things. Their salary has to be at least $30,000, and they have to have been at their job for at least 2 years. One simple if-else just isn't going to be enough to figure that out.
So how does the code deal with this? It's actually pretty clever. It just nests the decisions, one inside the other. Step 1, it asks, is the salary high enough? If the answer to that is no, game over. The application is denied right there. But if the answer is yes, then it moves on to a second question, inside the first one. Have they been on the job long enough? You only get the loan if you get a yes to both questions. That's what we call nested logic. All right, let's wrap this up. What do we learn? At the heart of every choice software makes, you've got these things called control structures. Basically, forks in the road. Our main tools are if for checking one condition and if-else for creating two clear paths. We figured out the secret to comparing text is that it's all just numbers underneath, thanks to ASCII. And maybe the coolest part is that we can stack these simple if statements together to build really complex logic.
And that kind of leaves us with one last big idea to chew on. We've seen that even something that feels complicated, like a loan application, really just boils down to a chain of simple yes or no questions. When you scale that concept up millions and millions of times, you get the incredibly complex software we all use every day. So here's the question. If even the most advanced artificial intelligence is built, at its very core, on these same simple binary choices, what does it actually say about the nature of intelligence itself? Just something to think about.